Imagine standing at the base of a tower so tall it vanishes into the sky. You crane your neck, but it stretches beyond the clouds, beyond the stratosphere, beyond Earth itself. The higher you look, the more impossible it seems. A structure, so colossal that it climbs all the way to space, yet somehow it doesn't collapse under its own weight. The air around you hums faintly as an enormous machine, a climber, begins its slow, methodical ascent, carrying cargo and passengers, inching its way toward the cosmos. There are no thunderous rocket engines, no fiery plumes, just a smooth, silent journey to the heavens. This isn't a scene from science fiction. It's an engineering dream, a vision that could one day become reality. What if we built a space elevator? Could it finally make space travel as routine as boarding a plane? Could it transform humanity into a true spacefaring civilization? Or is the sheer scale of such a structure simply too vast, too impractical, doomed from the start? To understand the need for a space elevator, we first have to recognize the problem with how we currently reach space. Right now, there's only one way: rockets. These towering behemoths must generate enough force to overcome Earth's gravity, requiring enormous amounts of fuel. Every single launch costs millions of dollars, and most of the rocket itself is discarded along the way. Massive boosters, external fuel tanks, entire sections of the spacecraft falling back to Earth or burning. Up in the atmosphere. Space travel is not only expensive, but incredibly inefficient. A single kilogram of cargo launched into orbit costs thousands of dollars. And while reusable rockets have brought costs down, they're still far from making space travel accessible for everyone. But what if there was another way? A way to bypass the chaos of rocket launches altogether, replacing explosive liftoff with something smooth, efficient, and cost-effective. This is the promise of the space elevator, a system that requires no massive explosions, no complex staging, just a continuous, stable connection between Earth and space. A system that, if built, could slash the cost of space travel by over 90%. The idea isn't new. In fact, it's older than modern spaceflight itself. The concept dates back to the late 19th century, when the Russian scientist Konstantin Tsiolkovsky first imagined a heavenly tower inspired by the Eiffel Tower. He envisioned a structure so tall it reached into the cosmos, a means of ascending to orbit without the need for rockets. But at the time, it was little more than fantasy. The materials needed to construct such a tower didn't exist. Nothing could withstand the immense forces acting upon such a structure. For decades, the idea remained locked in the realm of science fiction, appearing in novels and speculative engineering discussions. Then, in the latter half of the 20th century, something changed. As humanity developed real spaceflight capabilities, engineers began to take the idea more seriously. In the 1960s, Yuri Artsutanov and later NASA scientists expanded on the original concept. They realized that instead of a traditional tower, a structure that would collapse under its own weight, there was another way: a cable. Imagine a tether stretching from Earth's surface all the way into space, attached to a counterweight far beyond geostationary orbit. This cable, suspended in perfect equilibrium, would remain taut due to the balance between Earth's gravity pulling downward and centrifugal force pulling outward. If a climber could ascend this tether, we wouldn't need rockets at all. But even if this concept works in theory, what would it take to build one? First, we need the right material. Traditional steel, even the strongest alloys we have today, wouldn't work. It would snap under its own weight long before reaching space. The material needs to be not only strong, but also incredibly lightweight. This is where carbon nanotubes and graphene come in, materials many times stronger than steel, yet microscopic in scale. Scientists have theorized that a ribbon made from these materials, only a few centimeters wide but just atoms thick, could be strong enough to serve as the tether for a space elevator. But there's a problem. While we've successfully created small quantities of carbon nanotubes and graphene, we are nowhere near producing them at the scale required for a space elevator. The longest carbon nanotubes we can create today are just a few centimeters in length, far from the tens of thousands of kilometers needed for the elevator's tether. Until we crack the code on large-scale production, This remains the single greatest roadblock to making a space elevator a reality. Even if we solve the materials problem, there's the question of location. Where would we build it? The space elevator must be anchored at the equator. This is the only place where the forces acting on the tether will remain stable. But land-based, construction would be difficult due to geopolitical concerns. A more practical option? A floating platform in the middle of the Pacific Ocean where no single nation could claim ownership. The tether would extend straight upward, stretching past the atmosphere and deep into space, with the counterweight positioned at the perfect distance to keep the entire system in balance. But Earth is not a calm, unchanging place. The atmosphere is dynamic. Storms, hurricanes, earthquakes, even the Coriolis effect, all of these would put immense stress on the tether. Could we design a structure flexible enough to handle these forces without snapping? And that's just the challenges from Earth. What about threats from space? Micrometeorites, space debris, and even solar radiation could damage the tether over time. A single collision with an object traveling at orbital speeds, several kilometers per second, could sever the cable, sending it plummeting back to Earth in a catastrophic event. Could we build a maintenance system capable of repairing damage before it becomes a problem? Despite these challenges, space agencies and private companies are taking the concept seriously. Japan's Obayashi Corporation has outlined a plan to construct a space elevator by the 22nd century. NASA has conducted studies on the feasibility of space tethers. Even small-scale experiments, like testing high-altitude climbers on miniature versions of the concept, have already begun. Some scientists believe that if we can master the technology, a space elevator could become reality within the next 100 years. Others argue it's still beyond our capabilities, but if we could build it, it would change everything. Suddenly, space wouldn't be the domain of the ultra-wealthy or highly trained astronauts. It would be open to ordinary people. The cost of launching satellites, space stations, or even colonies on the Moon and Mars would drop dramatically. We could construct massive structures in orbit, factories, research stations, even shipyards for interstellar spacecraft, without relying on rockets. A space elevator could be the first step toward transforming humanity into a true interplanetary species. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. But before we get ahead of ourselves, what exactly would it take to build this thing? What kind of technology, planning, and sheer ingenuity would be required to turn this ambitious idea into reality? And if we manage to pull it off, what happens next? So let's say we do it. Let's say humanity manages to crack the code. Advances in material science finally give us a tether strong enough to stretch from Earth to space. The funding is secured, the engineers are ready, and the project begins. But where do we even start? How do you build something so vast, so unprecedented, that nothing in human history even comes close? The first challenge? Assembly. A space elevator wouldn't be built from the ground up like a skyscraper. Instead, it would have to be deployed from space downward, a concept that defies our usual way of thinking about construction. Imagine this: a spacecraft carrying a spool of ultra-strong tether is launched into orbit. From there, the tether is carefully unspooled, extending downward toward Earth while simultaneously extending upward to a counterweight in space. The entire system must be perfectly balanced. Too much weight in one direction, and the entire structure could drift off course or even snap. But before we get ahead of ourselves, let's talk about this counterweight. Why do we need it? Think of a space elevator like a giant spinning lasso tethered to the ground. Earth's rotation generates centrifugal force, pulling outward. If the tether extends beyond geostationary orbit, roughly 22,000 miles above Earth, this outward pull becomes strong enough to counteract gravity, keeping the tether taut. Without this counterweight, the entire structure would collapse. So what could serve as a counterweight? One possibility is an asteroid, literally capturing a small space rock and anchoring it to the tether. Another option, a massive space station, or a collection of spent rocket stages welded together into a heavy enough structure. Some even propose using the tether itself, gradually thickening the cable beyond geostationary orbit to provide enough mass to keep everything in place. Once the tether is in position, the next step is securing it to Earth. A floating platform in the Pacific Ocean would be an ideal anchor point, allowing adjustments for shifting ocean currents and minimizing damage from natural disasters. This station wouldn't just be an anchor, it would be a futuristic hub, serving as a launch pad for climbers, a research facility, and possibly even a tourism destination. Imagine boarding an elevator at sea level and knowing that in a matter of days you'd be stepping into the vacuum of space. But how would you travel up the elevator? Unlike a traditional elevator, there are no cables to pull you upward. This isn't a pulley system. Instead, climbers, robotic vehicles, would ascend using electric motors or other advanced propulsion systems, gripping the tether and slowly making their way into orbit. These climbers wouldn't be small either. Picture a massive capsule, perhaps the size of a passenger jet, capable of carrying cargo, satellites, and even human passengers. The journey wouldn't be instant. A climber moving at 200 miles per hour, far faster than any conventional elevator, would still take days to reach geostationary orbit. But compared to the violent, high-speed launch of a rocket, it would be a smooth, gradual ascent. No extreme G-forces, no risk of explosion, just a peaceful, breathtaking journey as Earth slowly shrinks below you, revealing the full curvature of the planet. And this is where things get really interesting. Unlike a rocket, which can only carry so much before fuel constraints become an issue, a space elevator could transport enormous payloads to orbit at a fraction of the cost. Need to build a massive space station? No problem. Want to send thousands of tons of supplies to a future moon colony? Easy. Dreaming of interstellar travel? A space elevator could be the perfect launch pad for ships designed to go beyond our solar system. But let's step back for a moment. There's still the question of safety. If something goes wrong, how catastrophic could it be? One of the biggest concerns is what happens if the tether snaps. It's easy to picture a disaster. Movie scenario. A massive cable whipping through the atmosphere, leveling entire cities. But in reality, it's a bit more complicated. If the break happens above geostationary orbit, the upper portion of the cable would drift into space, while the lower portion would collapse toward Earth. Most of it would burn up in the atmosphere, but some sections could survive re-entry and impact the surface. To mitigate this risk, engineers would design the tether with built-in failure points, ensuring that if it ever breaks, it fragments into smaller, less dangerous pieces. Another challenge? Space debris. Earth's orbit is already littered with old satellites and fragments of past missions, traveling at speeds of tens of thousands of miles per hour. Even a tiny piece of debris could punch a hole through the tether, weakening its integrity over time. To prevent this, a space elevator would require an advanced tracking system, using artificial intelligence to predict and avoid potential collisions. Then there's the question of geopolitics. A space elevator wouldn't just be an engineering marvel. It would be a strategic asset. The nation or company that builds it would have unprecedented control over space access. Would it be open to all humanity or monopolized by a select few? Would rival nations see it as a threat, leading to conflict? Could it even become the target of sabotage or terrorism? These are not just technical questions, but political ones. Ones that would need to be carefully addressed before construction ever begins. Despite all these challenges, the promise of a space elevator is simply too great to ignore. If we could build one, it wouldn't just change how we reach space, it would change everything. Suddenly, the moon becomes a viable colony, a stepping stone for deeper space exploration. Mars, once a distant dream, becomes reachable with regular shipments of supplies. Beyond that, the outer solar system, interstellar missions, the beginning of humanity's expansion beyond Earth. But before we can dream about our future among the stars, we have to ask, what happens once the elevator is operational? What new industries, economies, and possibilities would emerge? And could it really last? The space elevator is built. The tether stretches from a floating platform on Earth to a counterweight in orbit, held taut by the very force that governs planetary motion. It stands as humanity's most ambitious engineering marvel, an artificial bridge between Earth and the stars. But now comes the real test. What happens when we actually start using it? At first, the elevator's climbers, those massive robotic vehicles designed to scale the tether, would be tasked with ferrying supplies. Imagine cargo containers loaded with scientific instruments, habitat modules for space stations, and raw materials for construction. Unlike rockets, which are limited by the explosive nature of their fuel, the space elevator offers something unprecedented: the ability to transport virtually unlimited payloads at a fraction of the cost. And this is where things begin to change, economically, scientifically, and even culturally. The first and most immediate impact: the cost of accessing space plummets. Right now, sending cargo into orbit costs thousands of dollars per pound, making large-scale space operations prohibitively expensive. But a space elevator could bring that cost down to mere dollars per pound, revolutionizing the economics of space travel. Suddenly, space stations become easier to build, moon colonies become more than just theoretical, and even Mars missions become logistically feasible. Think about what this means for space-based industries. Mining asteroids for rare metals, something that sounds like pure science fiction today, becomes not just possible, but profitable. Manufacturing in microgravity, where delicate electronics and advanced materials can be crafted with unparalleled precision, becomes a booming industry. Space tourism, once reserved for the ultra-rich, turns into a mainstream experience, with passengers taking week-long trips up the tether to orbiting hotels, gazing down at Earth from a place few have ever seen. But beyond the economic revolution, there's something even bigger at play: the psychological shift in how humanity sees itself. Throughout history, every great expansion, whether it was the exploration of new continents or the first steps into flight, fundamentally changed human society. A space elevator would do the same. No longer would space be a domain of astronauts and government agencies. It would be accessible to scientists, entrepreneurs, artists, and even ordinary people. And this accessibility would lead to an explosion of scientific discovery. The International Space Station, for all its groundbreaking research, is limited by its reliance on rockets. Supplies are scarce, experiments are constrained by mass and volume limits, and crew rotations are infrequent. But with a space elevator, those constraints vanish. New space stations, far larger and more advanced than anything before, could be built with continuous shipments of supplies and personnel. Long-term human habitation in space would no longer be a question of feasibility, but a question of how soon. With these advancements, humanity would inevitably look beyond Earth orbit. The Moon, our closest neighbor, becomes the next logical step. A space elevator wouldn't just make moon missions easier, it would make them routine. Fuel depots could be set up in orbit, supplying lunar landers for regular cargo deliveries. The first lunar colony could be established not as a distant dream, but as an extension of the supply chain that starts at the base of the elevator. And then, Mars to human mission to Mars today is a logistical nightmare. Rockets must be massive. Fuel must be carried in enormous quantities, and every pound of cargo is carefully rationed. But a space elevator changes the equation entirely. With the ability to launch ships from geostationary orbit, where there's no atmospheric drag and no gravity well to fight, Mars missions become orders of magnitude easier. Spacecraft could be assembled in orbit, fueled efficiently, and launched with minimal energy. Imagine standing at the base of the elevator, watching as a massive interplanetary vessel is slowly lifted into space, piece by piece, before setting off on a journey to another world. It wouldn't be a one-time event. It would be the beginning of a new era. But for all its promise, a space elevator would also face challenges that go beyond engineering and logistics. The biggest question of all: would it survive long-term? The tether, despite being made of the strongest material ever developed, would be under constant strain, facing not only the forces of gravity and centrifugal force, but also external threats. Space debris, moving at tens of thousands of miles per hour, could strike the cable, weakening its integrity over time. Micrometeoroids, tiny grains of space dust traveling at hypersonic speeds, could slowly erode its surface. And then there's the risk of sabotage. A space elevator, by its very nature, would be a strategic and economic powerhouse. The nation or corporation that controls it would effectively control access to space. Would it become a point of geopolitical tension? Would rival factions attempt to destroy or disable it? Would its very existence lead to a new kind of space race, not for exploration but for control? To ensure its survival, the elevator would require constant monitoring. Automated repair drones would patrol the tether, scanning for damage and deploying nanomaterials to patch weak spots. Artificial intelligence systems would track every piece of space debris, making micro-adjustments to the tether's position to avoid collisions. Ground-based security systems would defend the anchor platform from potential threats, ensuring that no one could tamper with the foundation of humanity's new gateway to the stars. Yet, even with all these precautions, there's one final question. That lingers. What happens if the elevator fails? It's a terrifying thought. A catastrophic failure of the tether, whether from a sudden impact, a materials flaw, or deliberate sabotage, could send the entire structure collapsing. The upper half would drift into space, lost forever. The lower half, depending on where, it snaps. It could wrap around the planet, crashing into the ocean, or in a worst-case scenario, slamming into populated areas. Would the benefits of a space elevator outweigh these risks? Would humanity accept the possibility of disaster in exchange for unparalleled access to the cosmos? Or would fear hold us back from taking this final, monumental leap? One thing is certain: if we build it, it will change the course of human history. And yet, with so much at stake, we have to ask, are we truly ready? A space elevator is not just a structure, it's a paradigm shift. It represents the moment humanity truly steps beyond Earth, not in brief, daring leaps, but in a steady, unbroken climb toward the stars. And yet, for all the hope it brings, one question remains: will we ever actually build it? For decades, the idea of a space elevator has hovered at the edge of possibility, always tantalizingly close, yet just out of reach. The biggest obstacle? Materials. The tether must be made of something unimaginably strong, able to withstand immense tension, vibrations, and impacts, while remaining light enough to avoid collapsing under its own weight. Steel. Nowhere near strong enough. Kevlar. Not even close. Even the most advanced carbon fiber composites wouldn't survive. The only material that could possibly work is carbon nanotubes or graphene, exotic substances hundreds of times stronger than steel, yet nearly weightless at the molecular level, and that's where reality forces us to pause. As of now, we can create carbon nanotubes only in microscopic amounts. Producing them at the scale needed for a space elevator is beyond our current capabilities. But technology evolves, and materials science is advancing at a breathtaking pace. The question is no longer if we can create these materials, but when. Some experts predict that within the next few decades, we may finally reach the threshold where the impossible becomes feasible. But even if the material problem is solved, there's another issue: stability. The tether must endure the pull of gravity on one end and the outward centrifugal force on the other. It must survive the relentless assault of space debris, the searing radiation of the sun, and the occasional solar storm that could send waves of charged particles crashing into its surface. It must be actively monitored and maintained, repaired before minor damage turns catastrophic. And yet, despite all of this, engineers believe it can be done. Imagine the moment construction begins. The first strands of the tether spun in orbit and carefully lowered toward Earth. The counterweight, assembled piece by piece, slowly expanding into a vast structure at the edge of space. The climbers, robotic lifters designed to scale the tether, making their first slow, deliberate ascent, carrying components, modules, and eventually, people. The first passengers to ride the space elevator will experience something no human has ever known: a journey into orbit without the explosive violence of a rocket launch. The Earth will slowly recede below them, clouds swirling in an endless ballet of motion. Gravity will weaken until finally they step into the silence of space, not as astronauts, but as travelers, pioneers of a new age. And that is where the true revolution begins. A working space elevator will change everything. It won't just lower costs, it will transform our ambitions. No longer will space be a place we visit in brief, isolated missions. It will be a place we live, work, and explore continuously. Lunar bases will become supply depots. Martian colonies will be stocked with resources ferried effortlessly from Earth. Asteroid mining will cease to be science fiction and become the next gold rush. But perhaps the most profound change won't be technological. It will be psychological. For centuries, humans have looked up at the stars and dreamed. But with a space elevator, those dreams will no longer be confined to the realm of fantasy. Children born in the age of the space elevator will grow up knowing that the sky is no longer the limit. It is only the beginning. And yet, the biggest question of all remains. Will we have the courage to build it? Humanity has never lacked ambition, but great projects require great will. The space elevator is not just a technical challenge, it is a statement of intent, a declaration that we are ready to take our place among the stars. It will require international cooperation on an unprecedented scale, investment spanning generations, and a commitment to a future that many alive today will never see fully realized. So will we take the leap? Or will we let hesitation hold us back, bound to the surface of the world that gave us life, forever looking up but never reaching out? That choice is ours to make. And if you want to be part of the conversation, if you want to see a future where humanity reaches beyond Earth, make sure to like this video, share it with others, and drop a comment below. Do you think a space elevator will ever become reality? Or are the challenges simply too great? Let's talk about it. Because one thing is certain, the future is waiting.